In our everyday lives, there's going to be two major scales that we use for temperature. There's going to be degrees Fahrenheit if you live in the US, and there's going to be degrees Celsius if you live pretty much everywhere else. But even here in the US, when we drive past the bank, we see Fahrenheit, and then the thermometer gauge toggles over degrees Celsius for a minute. There's a third one that we use in the sciences a lot more often, and that is Kelvin. Notice I didn't say degrees Kelvin. We don't say degrees when we're talking about Kelvin. Now, Kelvin actually has an absolute zero for its minimal point. You can't go colder than absolute zero. And that's one of those ones where people philosophically want to recoil and say, well, there's got to be a way to go colder than absolute zero. But by the definitions, there aren't. If you remember that temperature is about kinetic energy and how much energy of motion you have in something, there's a such thing as standing still. That's zero. That's when there's no motion happening at the molecular level at all. If you suddenly had things start moving backward, whatever scale you're using, that would still be motion, and that's just going to be actually warming it back up. So the 0 point on the Kelvin scale really will be as cold as you can have because there won't be any motion happening down here. When you heat up to 0 degrees Celsius, also known as 32 degrees Fahrenheit, that would be the melting point of water. Now notice that we're using water as our benchmark. So 0 degrees Celsius is our freezing point, and we also know that 100 degrees Celsius is our boiling point. Well, in Fahrenheit, we know that freezing is 32 Fahrenheit, and 212 degrees Fahrenheit is boiling. Notice that these are 100 units apart, and that Fahrenheit is 180 units apart. That'll allow you to rebuild the conversion factors for these, though they'll generally be provided on exams and things. So we'll have 100 units apart for Celsius, we'll have 100 units apart for Kelvin, we'll have 180 units apart for Fahrenheit. That means that you're going to have 180 to 100 kind of be your conversion factor, and we have to make sure that we adjust our 0 point so they're all matching. Now, because of that, you got to make sure you do the math at the right time, and we'll mention that in just a moment. Celsius is not an SI unit technically, but it is widely and commonly used in science because it's the scale that matches up to our everyday life the most. In the laboratory, you'll be able to grab ice and make an ice bath that locks your temperature at 0 degrees Celsius. You'll be able to heat something up to 100 degrees Celsius when you boil it. And since we're commonly using water in our everyday life here on Earth, realistically we're going to use Celsius even though it's not our SI unit. But we will often have to convert into Kelvin to be able to do any further calculations with it. Now, the way that we convert between those is just to adjust our 0 point. We just subtract them. So we'll have to take that into account. We have to think about sig figs whenever we do a subtraction. Make sure you're using the correct rules for addition and subtraction whenever you're doing the conversion factor from Kelvin into degrees Celsius or vice versa. But since they're the same size, the math is pretty straightforward. But here's some practical advice I really want to emphasize. Only convert between Celsius and Kelvin at the beginning or end of the problem. If you do it in the middle, you're going to have big problems. A great example of that will be in the ideal gas law section. And when we are talking about the ideal gas law, I will bring up how that would destroy life as you know it and how you'd be basically creating a black hole if you get the math wrong. So make sure that you do your conversions at the beginning or end of the problem. And temperature will be an extensive property.